change of time variable, tau is nu t, and we let the excitation frequency nu equal to nu 0, which is a reference frequency, times 1 minus epsilon delta. Delta is the detuning parameter. And epsilon is a small parameter. Okay, and so we can rewrite the equation in this form with a small parameter epsilon on the right-hand side. Now, if we apply the transformation from Q prime to A and V, and we can get the differential equations in terms of the new variables A and phi. A is the amplitude and phi is the phase angle. We apply the method of averaging and find the averaged equation. Okay, so we only average for explicitly occurring tau. When the excitation frequency is not close to twice of the natural frequency of the system, and this is true, and the averaged equations are given by these two, and you can find the solution. So you can see the amplitude A bar is given by this exponential function, and because we have a negative e to the negative something t, so it approaches 0 when t approaches infinity. So this is stable. Now, when we have resonance, the excitation frequency is twice of the natural frequency. Okay, we can get the averaged equations. And you can look for the steady state solution. And obviously, we have A prime and phi prime equal to 0 for steady state solutions. Okay, now if A is 0, then Q is always 0. This is not interesting case because the response is always 0. Okay, so now we look for the solution with A not 0. And we can solve the equations to find something called amplitude frequency relation. Okay, so that's given by this equation. And on the left-hand side, it is the frequency ratio nu over 2 omega 0. And we have the steady state amplitude A0. Okay, so that's why it's called amplitude A0 and frequency relation. Okay, so now if you sketch this, you will have a diagram like this. Okay, so this part is when nu is close to twice of the natural frequency of the system. So in this region, it's unstable. And When it's unstable, the amplitude does not go to infinity. So depending on where is the frequency, excitation frequency, it corresponds to a steady state amplitude. If you choose another frequency, and then we have a different steady state amplitude. Okay, so we can perform an analysis to show that when the excitation frequency is outside of the resonance region, the zero solution is stable. When it's inside, when an excitation frequency is inside the resonance region, then we have a steady state amplitude. Okay, that's what this amplitude frequency relation tells us. Okay, so this blue curve is stable, but this part is unstable, and we can show it mathematically to prove that this part is unstable. Now we just want to show you and make sure you understand some basic concepts. Okay, now let's look at a special case when there's no damping. Okay, so undamped case. And for linear system, the system is unstable when it's inside this V-shaped region. Okay, now if you are given the amplitude of excitation mu, then we have this frequency band. And in this frequency band, the system will be unstable. Okay, so the system will be unstable. Okay, then this is the top figure we studied last week. And today we will look at the amplitude frequency relation. It's in the diagram below. Okay, so when we are in this region, the system is unstable. Okay, so corresponding to excitation frequency, because we have a nonlinear system, the response cannot grow to infinity. It will have a steady state amplitude. Okay, so now outside the resonance region, the solution is stable. Okay, so we look at the explanation. The amplitude relation is given by this. It's a simplified expression. So this gives us the blue curve. So when gamma is equal to 0, we have a linear system. It shows the top, okay? And when the excitation frequency is close to the twice of the natural frequency, we have an unstable region. For a nonlinear system, in the unstable region, the amplitude cannot grow to infinity. It will settle down to a steady state amplitude. Okay, but for a linear system, the amplitude of the solution will grow exponentially to infinity. Okay, so now we can study the stability of the steady state solutions. When the system is nonlinear, there are many methods that can be applied to study the stability of the steady state solutions. And for us, the most visually easier way is to plot the diagrams. We plot x and y. X is a cosine phi and y is a sine phi. We plot the response Q to illustrate the steady state solution. Okay, so we look at some simulation results. First, we consider an undamped system, so there's no damping. And amplitude frequency diagram relationship is given by these. Okay, so we have our initial condition Q0 is 0.01, Q dot 0 is 0. And the natural frequency of the system is 1. The excitation frequency is 1.8. Remember, we would have resonance when nu is approximately twice of omega 0 or 2. Okay, so, and in this case, it's 1.8, okay, much smaller than 2. So we are here at this red dot. And when we plot x and y are defined as this. Okay, so in terms of amplitude and the phase angle, we plot in the rectangular coordinates x and y. And this corresponds to this center. Okay, so this is called center. And since we have initial condition Q0 is 0.01, the solution x and y will go like this. Okay, so this is called something called phase portrait. And this is a very useful method when we study nonlinear dynamical system. Okay, and if you sketch Q, plot Q, then Q looks like this. Okay, so when there's no damping, we have this kind of phase portrait. Now still we consider no damping, but now nu is equal to exactly 2. Okay, so our frequency is at this point, and it corresponds to a non-zero amplitude. Okay, so here on the phase portrait, we have 3 equilibrium points, and these 2 are centers. And this is a saddle point. Okay, so if you look at it carefully, if your solution is here, then it will go to 0. Okay, so this part is stable. But if you shift a little bit, if you come here, then it will grow. Okay, so this point is a saddle point. And if we plot Q, and we have this. Okay, it's not quite easy to see when we have undamped system. And this is when nu is 2.1, so we are here, corresponds to this point. And the phase portrait corresponds to this. Okay, it's much easier to see when we look at a damped system. So here we have damping. And if nu is equal to 1.8, so we are here outside of the instability region. Okay, so the 0 solution is stable. 0 solution is stable. Okay, so the equilibrium point is the origin, and this is called a sink. It's called a sink because no matter where you start, if you start at this point with time t, you will go around and then come to the origin. If you start from Nenard point, if you have different initial condition, you will follow the solution and still come to this. Okay, so look at the solution. You can see we have Q0 is 0.01, so we start here 0.01, a non-zero initial condition. Okay, and the solution decays exponentially to 0. Okay, so you can see from the phase portrait also, for any initial condition, non-zero initial condition, the solution will go to the stable 0 solution. Okay, so the 0 solution is stable. Now if we change nu to 2, we are here. So it corresponds to a non-zero amplitude. Okay, so the phase portrait has 3 equilibrium points. One here, and the third one is here. Okay, now these 2 are sinks. and this is a saddle. Okay, so what it means is for any arbitrary initial condition, not on the, I explain that later. Okay, so for any arbitrary initial condition, you will go along this red line, okay, and then it will settle to this thing, okay, so with corresponds to this. Only when you have special cases, only when you are along these two curves, if you are here, you will go to the saddle point with time. And then if you are on this branch, you will go to you will leave it and then go to this sink. Okay, so this is saddle point. Saddle means it's like okay, so in this direction, it is stable. How do I draw a saddle quickly? Okay, so okay, so if you go along this direction, it's stable. Okay, so if you are at this point, and it's stable in this direction. When you go in this direction, it's unstable. Okay, so only for special initial conditions, you are on these two curves. But in general, you can see for other initial conditions, it always settles to a sink or this sink. Okay, so now this diagram is very good. So you can see initially we have initial condition 0.01. You start here, and then it will vibrate, okay? And then after some time, it settles to a steady state. Amplitude. Okay, so this part, you can see it goes this and then settle down to the steady state response. So this part would be called transient response. And steady state is 稳态. Okay? So if we have a linear system, the amplitude would increase exponentially to infinity. But when you have a nonlinear system, due to nonlinearity in the system, the solution cannot go to infinity, cannot go unbounded. So after some time, it will settle down to a steady state response. And we have a steady state amplitude determined by the frequency amplitude curve. Okay, so now let's look at Nanard undamped system. We have nu is 2.1. Nu is 2.1 corresponds to this point. Okay, so we have three solutions. 0 is stable, and this is stable. This is unstable. Okay, S stands for stable, U for unstable. Okay, so this purple corresponds to this, and yellow corresponds to this point and this point. Green corresponds to this. Okay, so the green is a zero solution. Okay, so this is a stable. You can see it's a sink. So if you start anywhere along the face portrait, it will go to this point. Okay, so these are all sinks. And the two purple ones are saddle point. Okay, so that means this is unstable, so we cannot have this. It will either, if you have zero initial condition, it will stay as 0. Okay, so if the initial condition is 0 and 0, then it will stay as 0. The solution is always 0. Now, if you have a non-zero initial condition, we start with 0.01. Okay, so if you start with a non-zero solution, you can see after the transient part, the solution will settle down to the steady state amplitude. Okay, so we will have this steady state response. Okay, so I hope you can visualize these two diagrams. Okay, so when you have a nonlinear system, the response cannot grow unbounded. After some transient part, the solution will settle down to a steady state response. And we have a steady state amplitude. It's determined by the frequency amplitude or amplitude frequency relationship. Okay, so in conclusion, in undergraduate mechanics, we studied static instability. When the static loading is equal to one of the critical values, we will have buckling. Okay, so here we have a beam under actual load. When the actual load P is equal to the first Euler buckling load, the beam buckles in the first mode. When P is equal to the second buckling load, the beam buckles in the second mode, and so on. And in the first half of the course, we studied mean resonance. For mean resonance, forcing term appears on the right-hand side of the equation of motion. And when the excitation frequency is close to the natural frequency of the system, we will have large response. And we need to memorize this diagram. It is the dynamic magnification factor. Okay, so when we look at the frequency ratio R equal to excitation frequency big omega over natural frequency omega 0, when this frequency ratio is close to 1, we have large amplitude of response. Okay, and actual resonance occurs only when we have zero damping. Okay, for undamped system, when omega is equal to the natural frequency of the system, we have resonance. And when we have resonance, amplitude of response grows linearly with time. Okay, the amplitude grows linearly with time. It only occurs at one frequency. Okay, only when omega is exactly the same as the natural frequency, we have resonance. And it has to be an undamped system. Otherwise, we will have no resonance. Okay. From last week and today, we introduced parametric resonance. For parametric resonance, the forcing term appears as a parameter on the left-hand side of the equation of motion. So for the buckling problem, instead of having a constant load, we have a dynamic load. Okay, now resonance occurs even when we have damping, and the resonance occurs not at a single frequency, but in a region of frequency. Okay, so when the excitation frequency is in the vicinity of twice of the natural frequency of the system, parametric resonance occurs. Okay, so if there's no damping, we have this V-shaped region. If there's damping, we have the yellow region. In the unstable region, the amplitude of response grows exponentially. So it's more dangerous, much more dangerous. even in the presence of damping, even when we have damping, the solution would grow exponentially. And today we look at the steady-state response of nonlinear system. In practice, the amplitude of response cannot grow to infinity when parametric resonance occurs because of nonlinearity of the system. Okay? As we know, for practical systems, linear system is usually approximation. Okay? And the response will reach steady state with large amplitude. So in the unstable region, for given excitation frequency, it corresponds to a steady state amplitude. Okay, so after some time, the response will settle down to the steady state response with large amplitude. Okay, so we only have a week to give you a brief introduction on dynamic stability or instability. And we cannot go into too much detail. There are various parametrically excited systems in engineering applications. We showed panels or foils in supersonic flow. Okay, so that's the airplane under wind load, or when it's flying, we have the supersonic flow. And then you can have pipes conveying fluid. And we can have a rotating shaft under compressive loads. Okay. So, and this is a shaft. And we will have a parametric excitation in the system. Okay, and a parametric resonance occurs under various types of dynamic loadings. We can have harmonic loading, that means sine or cosine, and it can be a periodic loading, or we can have random loading. Okay, we will study random loading in the second half of the course. And I only introduced you to one instability region. For a single degree of freedom system, parametric resonance occurs when the excitation frequency is in the vicinity of many instability regions. Okay, so if we plot this, it is nu over 2 omega 0. It will occur when it is close to 1. It's close to half. And then 1/3. And so on. Okay, so we only studied this yellow region. In fact, we have other regions, 1/2, 1/3, 1/4, 1/5, and so on. Okay, and but the instability regions become smaller and smaller. So it is important to focus on the first instability region. Okay, that's what I introduced to you. This is for a single degree of freedom system. For multiple degrees of freedom system, parametric resonance occurs when the frequency is in the vicinity of combinations of the natural frequencies. For example, if you have a 2 degrees of freedom system, we can have omega 1, omega 2 are the two natural frequencies. So when the excitation frequency is omega plus omega 2, we also have resonance. When it is absolute value of omega 1 minus omega 2, and we also have resonance. And these are called combination resonance. And if you have plus, it's called additive. That means plus. Okay, so when the excitation frequency is equal to sum of the natural frequencies, or this is differential. When the excitation frequency is equal to the difference of natural frequencies. Okay, we would also have instability, and we don't have time to talk about this in detail, but it's important to remember that if the excitation, the loading appears as a parameter, we have parametrically excited system. When we have parametrically excited system, if it's a single degree of freedom system, then when the excitation frequency is close to twice of the natural frequency, we have resonance. When we have resonance, if the system is linear, then the response grows exponentially. If it is a nonlinear system, the response cannot grow to infinity. It will settle down to a steady state response with a steady state amplitude. Okay, and if you have a more complex system, multiple degrees of freedom system, then we have other types of resonances, and it's more complex. Okay, so that's all on dynamic stability, and it's also the first half of our course, and we will take a break for 9 minutes. Please come back at 9 o'clock, and we will start the second part of the course on stochastic structural dynamics. Okay, please come back at 9 o'clock.
are you teaching today?
Yeah.
Okay.
It's a break.
Huh?
It's a break. I'm having a... Okay. So from now on, we will start the second part of the course on stochastic structure dynamics. It's also called a random vibration. With applications in earthquake engineering. Random vibration is quite a big topic, and we cannot study everything in random vibration. We will just study the parts that is relevant to earthquake engineering, because for civil engineering or structural engineering, the most important application of random vibration is in earthquake engineering, and sometimes also on wind engineering. But for this course, we will focus on So I will go quite slowly for this part. Okay, so if you have any problems or any feedbacks, please let Professor Tang know and he will convey it to me. Okay, now first we look at random processes. A random process is a continuous physical process influenced by non-deterministic. Deterministic means 确定性. So this physical process is influenced by non-deterministic factors. Okay, so for example, let's say we look at the wind load. On a building. Okay, so you can measure the wind load, let's say WT, from 8 a.m. to 10 a.m. Okay, so now if you measure yesterday, for 2 hours, you will find the wind load. They change like this, okay? And if you measure today, and you would have a different measurement from 8 a.m. to 9 a.m. to 10 a.m. Okay, so for each measurement, it's called a sample. Or a realization. Okay, so in the case experiment or in the case measurement, a random process, in this case, the wind load, generates a record, xkt. Okay, so we can say this is W1T, and this is W2T. And if we measure tomorrow, we will have W3T and so on. Okay, so if we perform measurements every day, we will have measurement every day. Okay, and each measurement is called a sample or a realization. Okay, so on the first measurement, it gives us a record or a sample, xkt. Okay, so this is called a realization or a sample function of the process. Okay, so the wind load between a time period is a random process. Okay, it changes with time t, but depending on when you measure it, you measure today from 8 to 10, you have one realization or one sample function for today. If you measure tomorrow, you will have of Nonlinear realization. Okay, so the random nature of the process is reflected in the fact that no two records are identical in every aspect. Okay, so for example, if we measure today, we will have we measured yesterday, we have something like this, and we measure today, we have a different realization. Okay, and then these two are not identical because of the random nature in the system. Okay, and we needed to use this diagram. Unfortunately, it's on a different page. Okay, so you measure the wind load. For day 1, you get this realization. You measure it on day 2, you get x2t. Measure it on day 3, you get a different measurement. Okay, together, each one is called a sample. And together is called ensemble. Okay, so all the realizations, all the sample functions together are called ensemble. Okay. Okay, the collection of all possible realizations of the random process is called ensemble of realizations. While each realization is a definite function of time t in the sense that xt for given k is an ordinary function for a fixed k. Okay, so if you measure today, you will get a record. Okay, you measure today, you will get a record, and this record is a fixed function. It's an ordinary function. But the ensemble of all realizations are not specific functions or fixed functions. They can be specified only statistically. Okay, so now for any particular value of t, xt is a random variable. Okay, let me explain this. So let's say we measure the wind load between 8 a.m. to say 10 a.m. Okay, so now this is 8:45 a.m. Okay, so for a specific T1, on day 1 we have a value. On day 2 we have a different value. On day 3 we have another value. Okay, so if you look at a specific T1, the wind load at this specific time is a random variable. Okay, so for fixed time, we have a value from record 1, a value from record 2, a value from record 3, and so on. Okay, so these values are the realizations of a specific random variable. And when it changes with time t, we have a random process. Okay, so a process 过程 is always related to time t. Okay, related with time. If there's no time, it cannot be called a process or a 过程. But for a specific time, it is a random variable. Okay, with different realizations. Okay, so for a particular value of time t, for fixed time t, a random process becomes a random variable. Okay, so it is a random variable when you fix the time t. A random process may be a function of a single variable, such as time. For example, the vertical displacement of the support of equipment is a function of time during an earthquake. It could also depend on several independent variables. The vertical acceleration of soil surface as a function of both time and location during an earthquake. Okay, so if you look at building, okay, so the ground motion here, the ground acceleration UG double dot T depends on only T, okay, because the foundation here is usually small and the variation is not that large. So the ground acceleration depends only on T. But it could also depend on both time and location during an earthquake. So for example, if you look at a bridge, and these are the bridge pairs. Okay, so that's a bridge. And that's UG double dot 1 at T, and this is UG double dot 2 at T. Okay, so basically this is x1 and x2 because the propagation of seismic waves, the ground acceleration at support 1 might be different from the ground acceleration at 2. So if we combine these two, you can say it's UG double dot. It's a function of x and t. Okay, so the ground acceleration depends on both time and location. Okay, so it is a function of two variables, location and time. And for some applications, it only depends on time. Okay, so a random process may be a function of a single variable or several variables. Okay, so now let's see how we can characterize a random process. A random process is described by its various probability distribution functions. Okay, so with respect to the figure 1.1 at a fixed time instant t, okay, so we have time t1. Suppose we fix at the time t1, we have different realizations. Okay, so you will have, you can plot a histogram or plot the values. We define first order probability distribution function f. We always use f for probability distribution function. Okay, so this is a fixed at time t. Okay, when we fix at time t, the probability distribution function is the probability. This P stands for probability. Xt less than x. Okay, in probability we studied that probability of x less than little x. This is small p is the probability density function. Okay, capital X stands for a random variable. Okay, and here x, big xt, stands for a random process. And x, small x, means a specific value that x can take. Okay, so if we look at a specific x, the probability that big X less than x is given by this area. So that's the probability x less than small x. And this is called a probability distribution function. And this curve is called the probability density function. Okay, so we use F for probability distribution function and little p for probability density function. Okay, so we define the first order probability distribution function like this. If the ensemble consists of total n sample functions, if we have n observations, out of which there are n realizations with x less than little x, then the first order probability distribution function is approximately this. Okay, so that's the definition of probability. For n large. Okay, so out of n big N examples or realizations. We have small n that many observations with values less than little x. Okay, then this gives us approximately the probability distribution function. Okay, so this is for one fixed time t. And now if we consider two time instances, t1 and t2, the probability that xt1 less than x1 and xt2 less than x2 is known as the second order probability distribution function. Okay, so we denote this way: f for distribution function, 2 stands for second order, and at t1 is less than x1, at t2 is less than x2. So it is defined as the probability that xt1 less than x1, xt2 less than x2. Okay, so now look at here. So we need to consider two time instances. At t1, we have these values. At t2, we have first value, second value, third value. Okay, so if we consider these two time instances, we want the probability that x at t1 is less than x1, x at t2 is less than x2. Now if we have total n examples, and we have n1, 2 that many examples with this condition, then the probability distribution function is defined as n1, 2 over n. Okay, so now if you consider one time, it's called first order. If you consider two time instances, we have second order. If you consider n time instances, okay, so t1, x1, t2, x2, tn, xn. So we have at time t1, x is less than x1. At time t2, x is less than x2. At time tn, x is less than xn. Okay, so this would be the nth order probability distribution function. A random process is said to be completely specified if its distribution functions of all orders are known. Okay, if we know the probability distribution functions, then we know the random process. Okay, now if you differentiate the probability distribution function, you get probability density function. This is similar to what we studied in probability. Okay, so the nth order derivative of the nth order distribution function gives us the nth order probability density function. Okay, so if we know the nth order probability density function for all values of n, then we know the random process. Okay, so the probability density function times dx1, dx2, dxn gives us this probability. The probability that xt1 is between x1 and x1 plus dx1. Okay, so this term. And xt2 between x2 and x2 plus dx2. Okay, so in general, the probability density function is the derivative of the probability distribution function. And the probability distribution function is the integral of the probability density function. Okay? Now, it is usually either unnecessary. Usually, it's impossible to specify the probability distribution functions of all orders. And usually, we don't have this information. For many practical purposes, the knowledge of only the first order and the second order probability distribution functions is sufficient. In particular, for Gaussian random process, the probability distribution function of the first two orders described process completely. Okay. In probability, we have normal random variable. Okay, if we have a normal random variable, it is determined by two parameters, the mean value mu and the standard deviation sigma. And the probability density function is 1 over square root 2 pi sigma e to the minus x minus mu squared over 2 sigma squared. Okay, x between minus infinity and plus infinity. Okay, so for 正态分布的随机变量, if we know the mean value mu and the standard deviation, then we know everything about the random variable. Okay, because the probability density function is completely defined by mean and standard deviation. Okay, so a Gaussian random process relates to normal random variable. Okay, so for a Gaussian random process, just Gauss now let's look at this. If this is a Gaussian random process, then these values for specific time, these values are random variables. And if the process is Gaussian, and this would be normal. Okay, so for each time t, the realizations are normally distributed random variables. Okay, so Gaussian means normal. Okay, so if we have a Gaussian random process. The probability distribution functions of the first two orders describe the process completely. We will look at this in section 1.1.6. If the probability distribution function are invariant under a change of time origin, so if you have T1, T2, and Tn, and then you shift it by tau, okay? If the probability distribution functions do not change for all orders of n and any value of tau, then the random process is called stationary. Stationary means 平稳. Okay, so that means the first order probability distribution function is independent of time. Okay, so if you have t, it's the same as t minus t, or t0. It is also the same as t plus t, or 2t. Okay, so for any value, it's the same. Therefore, if you consider all the time t's, it's independent of time t. Okay, so first order distribution function or probability density function is independent of time t. The second order probability distribution function depends only on the time difference. Okay, so you have T1, T2, you subtract T1, then T1 minus T1 is 0. And then it depends only on T2 minus T1, or a tau. Okay, so it depends on only one time, the difference between T1 and T2. Okay, that's for a stationary random process. Now these are the definitions of stationary 平稳随机过程. What does that mean? A random process can be expected to be stationary when the physical factors influencing it do not change with time. Okay? Intuitively, if the physical factors influencing the random process do not change with time. For example, the wind pressure on a building will be stationary when the wind flow is steady. Okay, so if you look at the wind load on a building, for a small, relatively short time period, it does not change. So it is a steady, it is a stationary random process. However, the ground acceleration of earthquake are non-stationary. So for earthquake, it usually has a build-up process, a build-up phase, a strong motion phase, and then a die-down phase. Okay, so for earthquake, it usually has a build-up phase, okay, and then a strong motion phase and then a decaying phase. So in this case, obviously, the behavior in the build-up phase is different from the behavior in the strong motion phase, and it's different from the die-down phase or the decaying phase. Okay, so in this case, you can expect that the random process is non-stationary, 非平稳. But if the physical factors influencing the random process do not change with time t, then we can reasonably model the random process as a stationary random process. Okay? And now we look at averages and moments. For many physical applications, it is extremely difficult to determine all the probability distribution functions from the available data. It is true for when we study random variables. Okay, for random processes, it's even more difficult. Furthermore, such detailed information is often unnecessary. Okay, so first, it's impossible, very difficult to find the probability distribution functions. Secondly, in most cases, it's unnecessary. Okay, so in these circumstances, one may have to be content, satisfied with knowing only certain average properties of the random process. Two types of averages can be defined for a random process, xt. Okay, the first is the ensemble average for a fixed value t of the time parameter, and we denote it as e xt. Okay, this e stands for expected value. (希望值 expected value or average 平均值. Okay, and you can use e brackets xt or use these angle brackets. I prefer to use these. Okay, and it's obtained by evaluating the average of the random variable xt over the ensemble of possible realizations. Okay, so for fixed t, you find the values of x for all samples, add them up and divide it by n. Okay, so in this diagram, we find this value from the first sample, this value from the second sample, this value from the third sample, and so on. Okay, so if we have total n samples, then we can add all the values up, then divide it by n. Okay, so that's the ensemble average or expected value. Okay, another average is the time average. And the time average is denoted by x bar. Okay, So ext or angle brackets xt denote ensemble average, and x bar t denotes time average. Okay, for time average, we only need one particular realization. We only need one sample, xkt, and we can compute the average over a large time period. Okay, so you integrate xt from 0 to t and divide by t. Okay, so this is the time average over time. Okay, so now give you a minute to think about which one is more difficult to evaluate. Ensemble average is much more difficult to evaluate because you would need a large number of samples. Okay, so in this case, to find ensemble average of the wind load at 8:45 a.m., we need to have records for many days, a large number of days, and then add up the values and find the average. Okay, but for time averaging, you only need one realization. Okay, and then you find the average over a long time. Okay, so this is much easier to measure. You can get the average between 8 a.m. to 10 a.m. or even 10 p.m. Okay, so you can just measure for one day and then take the average. But for ensemble averaging, going in this direction, you need to have records for many days. Okay, for time averaging, you only need one record, relatively long, then you can find the time. Okay, so make sure you understand the two types of averages, the ensemble average and the time average. Both these averages can be defined for any functions of a random process. The simplest of such functions are the polynomials. Okay, x to the power k1, x to the power k2 at time t2, x to the power kn at time tn. And the average of these, the expected value of these, are called moments. Okay, so you can define moments of any order. The most important of the moments obtained from the first order probability distribution are the mean value,均值 or expected value, 期望值, and mean square value. Okay, so mean square, that's mean, that's square. Okay, so the mean value we denoted by mu for mean, of random variable x, so that's the expected value of e of xt, so that's x times first order probability density function integrate from minus infinity to plus infinity. That gives us the mean value. Mean squared is the expected value of x squared. Okay, so mean squared. And it's x squared times the first order probability density function xt. And x RMS are called root mean square. Okay, so that's root mean square. Okay, this is a square root mean of square value. And we denoted it by x RMS for root mean square. And then you can define the variance of xt. We denote it by sigma x squared, or you can say it's variance VAR xt is the expected value of x minus the mean value squared. And if we expand this, it's expected value of x squared, mean square value minus mean value squared. Okay? And the sigma x is square root of variance xt is called standard deviation. Okay, so this is the same as what we have in random variable. Okay, so you have the mean value, variance, and the square root of variance is called standard deviation. Okay, so now if the mean value is 0, then we don't have this term. Therefore, standard deviation is square root of mean square value. So that means the root mean squared is the standard deviation. Okay, so if you have a stationary random process, the first order probability density function is independent of t. Therefore, there's no t in the probability density function. Therefore, we don't have t. Okay, so all of these averages are independent of t. If we have a stationary random process, okay, so the mean value, the root mean square value, or mean square value, the standard deviation are all independent of time t for stationary random variables, random processes. Okay? Okay, so we take a break here. Please come back at 10 o'clock. Okay, so we take a break till 10 o'clock. Okay, so we introduced the moments from the first order probability distribution function. Okay, and for first order, we have 1 time t. And if the process is stationary, then the results are independent of time t. Now we introduce correlation functions, and it is obtained from second order probability distribution function. Okay, when you have second order probability distribution function, that means we have 2 time instances, T1 and T2. Okay, that gives us the second order probability density function. And the most important average is the autocorrelation function. Okay, auto means 自 itself. And the correlation 相关 so autocorrelation function 是自相关函数. Okay, so here auto means the same random process, okay, but at 2 different time instances. So it's the expected value of x at t1 times x at t2, and it's denoted as r for relation. Okay, so we are dealing with the correlation function, and then x means auto for the same random process, and we could have r xy for 2 different random processes we will introduce in a moment. Okay, so for the same random process at 2 time instances, ext1 times xt2 is denoted as r xx, same x, at t1 and t2. Okay, so it's evaluated as x1 times x2, p2, the second order probability density function, then integrate with respect to x1 and x2. I missed integral sign, so minus infinity to plus infinity, because it's a double integral, so we need 2 integral signs. The prefix auto indicates that the 2 random variables considered xt1, t2 belong to the same random process. Okay, so that means itself. And a related quantity is the covariance. Yifangcha, defined by kxx, t1, t2. So the difference is if the random process is not 0, we have to minus mu1, and then minus mu2 for mu at time t2. Okay, so that's rxx t1 t2 minus mu1 times mu2. Okay, mu is the expected value of x, at ti. Mu I is the expected value at ti. Okay, the counterpart of the autocorrelation function is the cross. Correlation function, 互相关函数. Okay, so here we are dealing with two random processes, x and y. Okay, so we have r, x, y, two random processes, x at t1 and y at t2. Okay, so we need the second order probability density function of x and y at t1 and t2. Okay, in probability, we know that two random variables, x and y, are independent. If probability density function xy is p xx times py y. Okay, two random variables are independent. If this is called a joint probability density function is equal to pxx times pyy. Each one of these is called marginal. Probability density function. Okay, so here, two random processes, xt1 and yt2, are independent if the joint probability density function or the second order probability density function is the product of the first order probability density function. Okay, so if this is true, then the two random processes are called independent. Then this equation becomes...
should we drop the T1, T2, the subsecrets? Just say random process xt and yt are independent.
Oh, T1 and the T2 are here. Yeah, T1 and T2 are here. So that means x at T1 and y at T2 are independent.
Okay.
So at two different times. So for example, you have this is xt, and this is yt. So we have two random processes. Okay, so for example, this can be pressure. This can be temperature. And this can be, say, pressure. Okay, so now we have different times. So that's T1, and that's T2. Okay, so you're looking at two different times because each one is a random variable. And here it's another random variable. Okay, so when we deal with this, we are talking about a general non-stationary. Random processes. Okay, so if they are stationary, then you can drop out the time t. But if they are non-stationary, you have to be careful about the time t. Okay, so now because if they are independent, you can write the joint probability density function is the product of the marginal probability density functions. And then we obtain this result. The expected value of xt1, yt2 is expected value of x at t1 and expected value yt2. Okay, now let's look at a special case when we have a stationary random process. And for stationary random process, we only look at the time difference, T2 and T1. So we only need tau, which is T2 minus T1. The autocorrelation function depends on the time difference, T2 minus T1, and is usually denoted as Rxx tau. Okay, so this for stationary process becomes Rxx tau. So we only need the difference between T2 and T1. Okay, without loss of generality, suppose that xt has 0 mean value. So we suppose the process has 0 mean value. Then the autocorrelation function Rxx tau has the following properties. The autocorrelation function at 0 is okay, this is the definition of the autocorrelation function. So when tau is 0, it becomes Ex squared. Okay, so that's the mean square value or the standard deviation squared. Okay, so the autocorrelation function at 0 is equal to the mean square value of x. This is a very important property. And the autocorrelation function is symmetric about tau equal to 0. That means Rxx tau is the same as Rxx minus tau. And it can be shown that Rxx0 is always larger than or equal to Rxx tau. Therefore, the first order derivative of the autocorrelation function, if it exists, must be 0. And second order derivative must be negative because maximum okay, so that's tau, and this is rxx tau. And we want that the zero value is maximum. Okay, so therefore the first order derivative is 0, and the second order derivative, which is the curvature, must be negative. Now, if there's no periodic component, then rxx tau equal to 0 when tau approaches plus or minus infinity. Okay, so it goes to 0 when tau is large. Okay, a very, very important relationship is the following. Rxx tau is the full inverse Fourier transform of Sxx omega, or define this, and so Rxx tau is the inverse Fourier transform of Sxx omega. Where Sxx is a real positive even function of frequency omega. It's real, positive, even function of omega. Okay, so even function means it's symmetric about omega equal to 0. So that's Sx omega, and it's real and positive. Okay, even, or it can be like this. Okay, as long as it's symmetric about omega equal to 0 axis. Okay, so the autocorrelation function is the inverse Fourier transform of the Sxx. Therefore, Sx is the Fourier transform of the autocorrelation function. Okay, so Rxx and Sxx are a pair of Fourier transforms. Okay, and Sxx omega is known as the power spectral density function, PSD, power spectral density function of the random process. So these two equations connect the autocorrelation function and the power spectral density function of stationary random process. And we will explain the meaning of power spectral density function in detail in the following. Okay, so that's very important. Autocorrelation function and the power spectral density function are related by Fourier transforms. Okay, so let's look at a few examples first. If the autocorrelation function is say a periodic sinusoidal function, okay, so the power spectral density function are two Dirac delta functions. at omega 0 and minus omega 0. Okay, if this is cosine omega 0 tau. And if Rxx is of this form, exponentially decaying, and with parameters alpha equal to alpha 1, alpha 2, alpha 3, then Sxx is something like this. Okay, so for alpha 3, the autocorrelation function is very narrow. And the corresponding pole spectral density function is more flat. Okay, now for the special case, when the power spectral density function is a constant, the correlation function becomes a delta function. Okay, so now let's explain what's the meaning of power spectral density function. We look at the mean square value. This is the mean square value. It is the autocorrelation function evaluated at 0. Okay, so that comes from this property. Okay, the autocorrelation function at 0 is equal to the mean square value. Okay, then you substitute 0 into the inverse Fourier transform, you obtain something like this. And you can change to, this is the circular frequency. And F is the real frequency. Okay, so normally it's in hertz. Okay, so mean square value is equal to this integral. Okay, so now what's the meaning of expected value of x squared? If x is considered as a current in an electrical circuit, okay, if R is the resistance, 是个电阻, and I is the current. And V is the voltage. Okay, so I times V is the power. Okay, and then we know that I is equal to V over R, or V is equal to I times R. Okay, so you can rewrite this as replace V by IR, so that's I squared R. Or it is the same as V squared divided by R. Okay, so In this case, I squared or V squared are related to power. Okay, so if X is the current in an electrical circuit, then I squared is related to the power, okay? And expected value means the average power dissipated in a unit resistor. And from this, Sxx is the contribution to this power at the frequency f from a bandwidth df. Okay, so this function is called power spectral density function, because this is related to power, and power is 功率. Spectral means related to spectrum. Spectral is adjective and spectrum is noun, okay? So power spectral density function means 功率. Okay, so that's the distribution of the power for frequency f. Okay, so if we integrate over the entire frequency range, we get the total power. Okay, so Sxxf df is the contribution of frequency f over width df. Okay, and then if you integrate, it's over the entire frequency range. Okay, so if we look here, you have f over a df so this would be the contribution of f over df to the power. Okay, power is x squared, or average power, because we are taking the expected value. Okay, so because of this property, this function is called a power spectral density function. Okay, so that's the how the term power spectral density come from. Okay, so let's go back to this. When the power spectral density function has only a delta function or two delta functions, so that means we only have one frequency component at omega 0. Okay, so that means xt is a sinusoidal function. It only has one frequency component. Okay, now, on the other hand, if you have this case, what does that mean? The power spectral density function is a constant over the entire frequency range. Okay, so that means we have constant contribution from all frequency components. Okay, and in physics, this is called 白噪声 or white noise. Process. Okay, when you have all frequencies, you get a white noise or 白噪声. Okay, and then corresponding to a white noise process, the correlation function is a delta function. So that means the value at this time is not correlated to different time, okay? Because when you have a value for any other value tau, the correlation is 0. So for white noise, the power spectral density function is a constant. The corresponding autocorrelation function is a delta function. Now somewhere in between, we have this case. Okay, so for the blue, the power is focused relatively over a narrow range. Okay, so we call this narrow band random process. Narrow means 窄. Band means ping, frequency band. Okay, narrow band. And for alpha 3, the power is over a wider frequency range. Okay, so we call this a wide band random process. Quanping. Okay, then alpha 2 is somewhere in between. Okay, so when the power spectral density function is focused or concentrated over a narrow frequency band, it's called a narrow band random process. When the power spectral density function has a relatively flat value over a wide frequency band, then it's called wide band random process. Okay, so we have the explanation here for periodic function. The correlation function is a periodic function. The power spectral density function includes 2 delta functions. And for exponentially correlated autocorrelation function, you have the corresponding power spectral density function. So depending on the value of alpha, You could have a wide band process or a narrow band process. Okay, now for a white noise process, the power spectral density is a constant. The autocorrelation function is a delta function. So that means the power spectral density of a white noise is constant over all frequencies. A white noise process is clearly not physically realizable because its total power is infinity, okay? However, it is convenient mathematically. It is a convenient mathematical idealization for a process whose power spectral density function remains practically constant over a wide band of frequency. We will study this next week. So I will stop here for today. And thank you very much. Have a great day.谢谢。